So we shall make a recording, and then I will put it onto YouTube, and in the next mail you will receive the data to how to reach this. And so I will give a kind of introduction, which you may, which I am sure you will improve. So in general, people do not care about the fact that in the kinetic differential equations, the reaction rate constants occur more than once. So the parameters of the right-hand side are not independent, they are dependent. And this is a fact which should be taken into consideration. And I think this will be one of the points we shall hear about. So please, Oscar, start with a very short introduction. Not everybody may know you, and then go ahead.
All right. Thank you, Janos, for the invitation to speak here. This is my first time in this seminar, actually, but it seems very, very nice, and I hope to attend many more talks in the future. So yes, I'm Oscar Henriksson. I'm a PhD student in mathematics at the University of Copenhagen with Alexandra Feliu as my advisor. And my specialization is in algebraic geometry, but I'm also very interested in problems that come from reality, and especially from biology. And that's what has led me to do some work on chemical reaction networks. And some of that is what I will talk about today. I know this is a very mixed audience with people who are I see some people in the audience who are experts on this type of mathematics, but I also imagine that there are people who are more interested in, well, other aspects of chemical reaction networks. So I think it's fair if you interrupt me at any point throughout the talk, if something should be clarified, or if I'm overseeing something that should be explained more properly. So just ask questions. I might not be able to see the chat so easily, so somebody should notify me if there is a question that comes up. Okay. And with that, maybe we should start. So what I will talk about is joint work with my advisor, Alexandra, and our collaborator, Beatriz, who is in Madrid, in Spain. And it's part of it is already on the archive. This is a more mathematical paper, but we're also working on a paper that's more focused on the application to reaction network theory, and that will hopefully be on the archive soon, but it's not quite there yet. Yes, so maybe we should begin by saying something about what we mean by steady states in this context. So the setup that I imagine is that we have some sort of chemical reaction network taken with mass action kinetics, or even generalized mass action kinetics, for those of you who like that. And the steady state in a certain compatibility class will be given by a polynomial system that looks something like this. So there will be some part that comes from setting the right-hand sides in the ODEs that you get when you model this with mass action kinetics to 0. So that's these polynomials. And there will be some part that corresponds to conservation laws. And there are some matrices that sort of encode the structure of this system. We have a stoichiometric matrix, a kinetic matrix, and a matrix of conserved quantities. And there are some variables, which are the concentrations of the different species that appear in the network. We have some rate constants, one rate constant for each reaction, so R in total, and a couple of total amounts, so one for each sort of linearly independent conservation law that we have picked here. And just to give an example of how this works, exactly how these matrices work is maybe not so important for the talk, but they will appear, well, throughout. So it's maybe good to take a deep breath here and sort of try to internalize as much as possible of this notation. So for example, in this case, for this system, the matrices that encode the system are these three. So for example, there is one column for each reactant complex, so one for each reaction. This column here corresponds to this monomial here. This corresponds to this this monomial. This monomial corresponds to this column, and so on. And we have one row for in the W matrix for each conserved quantity. So in this case, it's just x1 plus x2 plus x3. Yes. And geometrically, we have some sort of zero locus of this that I will call the steady state variety, which is in this case this blue curve, and the stoichiometric compatibility classes will be an affine linear space. Okay. Are there any questions or concerns at this point?
I wonder if you will ever use that the conservation laws are mostly defined by the left node space of n.
Exactly.
So, but will it be used any time later?
Actually, no, that's a good point. So most of what I will talk about, most of the algebra that we'll get into is quite flexible in the sense that this B, for example, the kinetic matrix doesn't have to come from the stoichiometry of the network. So we can do really generalized mass action kinetics. And the W can also, it doesn't really have to come from the left kernel of n. We can do any W here, and the sort of algebraic conditions I will get to will still work. So this is a quite general theory that works for any, we call this vertically parametrized system, because there are, like you said in the beginning, there are some repetitions of the parameters, the rate constants, but they always appear vertically if you imagine that you write out the coefficient matrix for the system. So the K3 is repeated here, but it always appears in front of the same monomial. So we call this vertically parameterized systems. And this paper that we have on the archive gives a sort of a general theory for how to understand the generic geometry of these systems. So we're going to be quite flexible. But feel free to think of this as the usual stoichiometric matrix, this being the usual reactant matrix, and this being like a usual choice of basis for the left kernel of the stoichiometric matrix. But it doesn't have to be like that. And at the very end, we will actually use this flexibility to our advantage to say something about absolute concentration robustness, if time permits. Okay. Are there any other issues or questions here? If not, let's move on and sort of, so I'll give, I guess I have one piece of bad news about the geometry of this blue part, and then I have some good news. And the bad news is that these systems are universal in the sense that if you take any system of polynomials in n variables and look at the positive steady states or the positive solutions, you can find a network with a steady state system F and some choice of rate constants such that the positive solutions of the given system is equal to the positive steady states of this network. So that means that networks, positive steady states are as complicated as studying completely general systems of polynomial equations in the positive orthant. And that's a pretty daunting task, which we will probably not be able to say that much about. And just to sort of, I guess this is quite well known, but just to sort of remind ourselves why this is true, because I think it's an important philosophical point to make, is that we can take this system, we can multiply by some appropriate monomials. For example, we can multiply the first equation by x1 and the s equation by xs, and then we'll get rid of these so-called negative cross effects, and then Janusz's and harsh realizability condition, also known as the Hungarian lemma, kicks in and tells you that this will come from a reaction network with a specific choice of rate constants. If we have more than n equations, more than n polynomials, we need to do a small trick, but it's not very complicated. And the trick is just that instead of writing out all the s polynomials, we can just mash together the last ones into a single polynomial because the positive solutions of these polynomials is going to be the same as the positive solutions of this, right? If you have a sum of squares, the only way this can be 0 is if each individual term appearing is 0. Okay, and then you can apply this classical trick and refer to the Harsdorff realizability condition. Okay, so these are the bad news. Steady states are complicated, and for example, this means that we can have very complicated, we can have as complicated geometry of a steady state variety as we can achieve by any polynomial system. In particular, we can have non-smooth points where we don't have a well-defined tangent space. We can have components of many different dimensions, and algebraically this corresponds to the Jacobian having less than full rank of these pathologies. And just to give an example, we can have something crazy like a circle and a line passing through the circle and some points. This would involve non-smooth points. It would involve mixed dimension, where most of the variety would be positive or one-dimensional, and then we would have something that's zero-dimensional. And this is quite pathological from a geometric point of view. And but the good news is that whenever you take the k parameter that realizes something like this and just perturb it a little bit, all these pathologies will vanish. And I guess seeing is believing. So let me show you an animation. So here we have a simpler case where we only have a circle and a line. We can realize this is coming from a network by writing the equations like this. So this would be the network if you use the sort of the canonical realization from the Hungarian lemma. And if we now just start to perturb these coefficients, we see that immediately all the pathologies disappear, and we get something that's essentially always smooth and of a single dimension, in this case, dimension 1. So that's, I think, the good news. And what I will do next is to sort of make this precise. Okay. So go back to the slides and say that the point is that we have these parameters. So typically when we have a network, we have these parameters, they are unknown, and they naturally fluctuate with temperature. So it makes sense to study this as a parametric system, and there will be a landscape in parameter space with different behaviors. There are methods for sort of completely mapping out this parameter landscape, but they are very expensive. So here I took another network and just ran something called a cylindrical algebraic decomposition of parameter space. In this case, there were 2 parameters, and there were 2 regions where we had different behaviors. I think in this case, I just counted the number of connected components. This is something you in principle can do, but it's very expensive. And sort of the approach that we take, or that I take in my work, is that I try to say more, sort of paint a broader picture of parameter space by saying something like that we have a certain property for some parameters, or in a Euclidean open subset, or generically in the sense that it holds everywhere in parameter space except on a lower dimensional subset, or even better, that some things hold for all parameters. Typically this is very hard, and typically the mathematics comes out much more nicely in these scenarios. And these are, in a sense, also what's biologically perhaps most meaningful, since there naturally are these fluctuations in the parameters that come from temperature dependence and other environmental dependencies. So that's somehow the motto that sort of will follow us throughout this talk, that it's the behavior in regions like this that is the most biologically relevant, and things turn out to be much more well behaved if we focus on sort of the behavior up to these perturbations. Okay, so a mathematical result then. So this is, I guess, our first main theorem in this line of work, and it's telling you that the crucial thing to look at when you try to understand the geometry of the steady states for generic choices of the rate constants is that you should look at the rank of the Jacobian. Okay? And we will say that a reaction network is non-degenerate if there is some choice of rate constants and some steady state for this choice of rate constant, such that the rank is the maximal possible one, which is the rank of the network, the rank of the stoichiometric matrix. Okay, and luckily for us, it's quite easy to explicitly write out what the Jacobian looks like. It's simply this product of matrices. So depending on what areas of chemical reaction network theory you're interested in, you might very well have seen this expression before. Furthermore, checking that there is such a k and such an x amounts to checking something that can be formulated as a purely linear algebra condition. So, well, first of all, we need the positive kernel of the stoichiometric matrix to be non-empty, because otherwise there simply won't be any positive steady states at all. And then what we need to check is that the product of the stoichiometric matrix with the diagonal matrix that come from something in its kernel times the transpose of the kinetic matrix well, has this maximal rank. And this can be done very easily computationally, in the sense that if this is true for some W in the kernel, then it's true for almost all W's in the kernel. So you can do this probabilistically, just pick something in the kernel, and with probability 1, you will detect this if it's true. And if it's not true, you can certify that it's not true for any W in the kernel by simply parametrizing the kernel and then looking at evaluating the minors of this matrix symbolically. Okay, so this is computer friendly, and it dictates the generic behavior of these solution sets in the following sense. So there are two cases. If this is true, then the set of then a lot of nice things are true. In particular, the set of all rate constants for which there are positive steady states at all is going to be full dimensional. So there will be an open subset in parameter space where we have solutions. And for almost all values in this nice set, the steady state variety will be completely smooth. It will be manifold. It will have a well-defined tangent space at every point. And the dimension will be the same everywhere for almost all such rate constants. Okay, so we can just draw a small sketch of parameter space to help us. So here I imagine that there are two rate constants. Of course, there are probably many more, but we're a bit limited in what we can draw on a computer screen. So we have this parameter space. There will be some nice full dimensional subset where there are solutions. Okay, and outside here in the gray area, I imagine that there are not any solutions, but there will be some open subset in parameter space where there are solutions. And for almost all of them, we will have these blue nice properties of smoothness and pure dimension. But there could be some exceptional lower dimensional set inside here where something goes wrong with either the smoothness or the dimension. And that's exactly what we saw in this animation I showed you a few slides ago, where for very specific choices of parameters, we had this weird circle that was intersected by a line, which sort of broke the smoothness. But as soon as we just perturbed a little bit away from that choice of parameters, we were in the nice setting. So this was an example of a network that is non-degenerate in this sense. Okay, the other case is that this is not true, and then we're in a really pathological setting where, first of all, there are no steady states for most choices of rate constants. So the set of rate constants for which there are steady states, positive steady states, is going to be a small lower dimensional subset of parameter space. Okay, and whenever we are in this lower dimensional subset of parameter space where there are steady states, then all of them will be pathological in the sense that the Jacobian is going to be singular. So it could be that we don't have smoothness, or it could be that something is wrong with the dimension, or that something else is dysfunctional. So if we draw a sketch of the parameter space in this case, it means that almost everywhere we're in this gray scenario where there are no positive steady states at all. And there might be a small exceptional set where there are positive steady states, but then we always have a problematic Jacobian. Okay, so these are the two scenarios, and this means that we cannot have pathologies in an open subset of parameter space. Either we're here, and then when we perturb, we end up with nice geometry, or we're in this setting, and then when we perturb, we get an empty steady state variety. Okay, that's the message of this slide. Are there any questions, or is the notation clear enough, or should I maybe recall something?
Nice.
Can you just repeat what you mean by pure dimension?
By that I mean that at every point in the steady state variety, we have the same dimension. So if I go back to I have an example here where we don't have pure dimension. So here the positive zeros of this messy polynomial product is going to consist of a circle that's one-dimensional, a line that's one-dimensional, and a point that is zero-dimensional. So here we
I think this is a good example. So if the point wasn't there, is it okay, but there's some intersections where you have like two lines?
Yeah, so then in this
still like one dimension.
Yeah, if we didn't have the point, if we didn't have the point, then this would be pure dimensional, but it would still not be smooth because it would have these self-intersection points where there is no well-defined tangent space. So this would still be pathological. So it would have one of the pathologies that I'm talking about. But yeah, there are two kinds of pathologies that I'm talking about. One is having mixed dimension, and one is having points where there is no well-defined tangent space. So yeah, and none of these pathologies can happen in like an open region of parameter space, because either we're here, and then when we perturb the parameters, we will have something that's completely smooth without any weird self-intersections, and we will have pure dimension, so there will be none of this mixed dimension business. Or we're in this case, and then when we perturb, the steady state, the positive steady states completely disappear when we do the perturbation.
Sorry, can you go back to this VFK just 1 minute, then you record it again?
Yes. So this is so FK is the steady state system. So the part that comes from the right-hand sides of the ODEs for a specific choice of K. So this set, for example, is all choices of rate constants such that when we plug in these rate constants in our steady state system, we will have positive solutions.
Okay,
so
thank you.
the positive is the positive solutions of this polynomial system.
Yeah, thanks. There are too many notations. Yeah, thank you.
Yes. Okay, so Z is the set of rate constants where there are positive steady states at all. Yeah. This means positive solutions. This means steady state system where we have plugged in a choice of rate constants. What we should look at is the Jacobian, which depends on the stoichiometric matrix and the kinetic matrix. Okay. I'll move on and give an example of where this has been asked previously in the literature. So there is this very interesting paper by Balázs and George and Polly, where they construct certain networks that have unexpectedly high dimension of the steady state variety for specific choices of rate constants. So here we have a network where if they pick these particular values of the rate constants, the steady state variety looks like this. So there's a point and this round one-dimensional thing. So this is something I would call pathological, because first of all, we have different dimensions. It's also not the dimension that you would expect, because this is a full rank network. So there are 2 species, and the stoichiometric matrix will have rank 2. So you would really expect the steady state variety to be 0-dimensional, to consist of finitely many points. But we have this whole cycle here. So this is pathological. And they ask, is it possible to construct something like this such that we have this incorrect higher than expected dimension for a case in an open subset of parameter space? And as we just saw on the previous slide, this is not possible. So I guess that's a bit reassuring that that cannot happen. And indeed, in this example that they constructed, they observed that if you just perturb a little bit, you will break this pathological behavior, and you will just have finitely many points. Okay, so this cannot happen. We cannot have an open subset in parameter space where we have pathology like this. Okay, so that's I guess the first piece of good news that I have. Let's maybe continue and give an example of how this can be a quite, I mean, it's a simple, but I think illuminating analysis that you can make. So imagine that we have this model, this network, that describes how the HIV virus interacts with the human immune system. So I guess V stands for virus, and T stands for T cells, and M stands for macrophages, and I stands for infected. So yeah, it's a reaction network that you can model with mass action kinetics. And if we do this analysis, so we look at these matrices and their ranks, we see that that we do indeed satisfy this rank condition I had on I showed 2 slides ago for almost all values of all choices of elements in the kernel. We can also see that the stoichiometric matrix does indeed have positive elements in its kernel. And that means that there will be some open, nice region in parameter space where we have, in this case, finitely many steady states, because this is a network of full rank. So the sort of this expected dimension that we'll have for almost all choices of rate constants is 0. So we will have something 0-dimensional. There will be finitely many points. And this will happen in an open region in parameter space. And indeed, that's sort of the purpose of this model that they sort of introduce in this paper, that they want to introduce a model that can account for the possibility that the HIV virus coexists with the immune system in some sort of equilibrium. And this simple rank condition is a quick way to detect that it has that desired property. And we can also, just for fun, imagine what happens if we change the model a little bit. So we remove this the ability for the immune system to produce new T cells and macrophages, and then of course it's maybe not so unexpected that the story changes. So now the rank condition is not satisfied, but we do still have positive steady states for some choices of rate constants. So that means that the parameter space will look something like this. For most choices of rate constants, there won't be any positive steady states. So the only steady states will be that either the immune system wins or the virus wins, and something goes extinct. But there will be some exceptional subset of parameter space where there are positive steady states. But then things will be slightly pathological in the sense that the Jacobian will have less than expected rank. Okay, so this is a quick computational thing you can check when you have a network. But you can also prove sort of general things about classes of networks. So many many well-known classes of networks will satisfy this rank condition.
Excuse me,
For example.
could you go back, please?
Yes, yes.
So what if you also discard the outflow reactions?
If I did what?
If you discard all the outflows,
I see.
what happens?
Because
in first step, you discarded the inflows. And
yes.
what if you discard this too?
That's a good question.
It will not
and
be a mass conserving system still, but
yes, yes.
okay.
Yes, it's not immediate to me what happens with this. But I would imagine that either one of these will probably fail. I don't think you can have positive steady states without these outflows. That's my my guess. But this is it's a simple calculation to check. So maybe an exercise for all of us to see if we understood this. To do this after the talk. Okay. Yes, so there are classes of networks that satisfy this rank condition. So, for example, all weakly reversible networks satisfy this. This is due to a result by Balázs that says that there will be positive steady states for all networks. We must be in this nice scenario because, well, the region where we have positive steady states will be full dimensional. Also, if you have conservative networks without so-called relevant boundary steady states, then you can do like a topological argument to convince yourself that we must be in this setting. If the network is consistent and satisfy Feinberg's deficiency 1 theorem, we're also in this setting. Injectivity, for those of you who know what that is also sufficient. Yeah, so there are big classes of networks that fall into this this nice, less pathological scenario. So that's, I guess, also reassuring. Okay. I'll say something about a couple of refinements you can make of this result. First of all, there is nothing stopping us really from using rational exponents. The tools we use to prove our condition, of course, they rely on algebraic geometry, which works for polynomials. But if we're only interested in the positive orphant, we can do sort of some quite simple changes of coordinates to turn a system with rational exponents to a system with polynomial, that is a proper polynomial system, by simply clearing denominators by making a change of coordinates. So we do this. So we sort of look at each variable and look at sort of the least common multiplier of all denominators that appear in the exponent of that variable. And then we just do a change of coordinates that clears these denominators. And then we get the new system. And nothing about sort of the rank condition will change just because we have changed the exponents like this. So this property is preserved by this type of change of coordinates. So that means that we can still use the rank condition to decide whether we're in this setting or the very pathological setting. From this type of analysis, we also see that if we are in the nice setting where the rank condition is satisfied, then we will be there also if we slightly perturb the exponents of our system, and that corresponds to slightly perturbing the kinetics a little bit. So sometimes the exponents are based on experiments, and then there are inherent uncertainties, but this doesn't matter so much. So if we are in the non-pathological setting, then we will still be there after small perturbations in the kinetics. So that's also a piece of good news, I guess. I'll also quickly say something. So this will look a little bit more messy, but what happens if we take into account the stoichiometric compatibility classes, so the conservation laws? if we include them in the system, we get an effectively square system, because here we have effectively, as many independent equations as the rank of the network, and here we have one equation for sort of each element in the left kernel. So together we get an effectively square system, and we would expect finitely many solutions. And a similar rank condition, so a completely analogous rank condition, can be used to check whether we have generically finitely many solutions or whether we have infinitely many solutions. And the result looks like this. So instead of checking the rank of this thing, we check the rank of a slightly bigger matrix that comes from including this in the Jacobian. And we can turn this into something that's more computer friendly in a very similar way. And then the two cases are as follows. So if we are non-degenerate with respect to the compatibility classes in this sense, then the set of rate constants and total amounts for which we have positive steady states in that compatibility class will again be a full dimensional set. And for almost all choices of parameters in that set, there should be a W here, sorry, we have finitely many. So again, there is a nice open subset of parameter space such that almost everywhere in here we have the expected behavior, which is to have finitely many steady states in each compatibility class. But there is also a non-degenerate situation where this rank condition is not satisfied, and then the set of parameters, so K's and C's, for which we have positive steady states, is going to be a small lower dimensional subset, and everywhere inside this subset, all the steady states are pathological in the sense that the Jacobian is singular, and that could, for example, be because there are infinitely many. So again, there are these two scenarios. This is a bit more technical, but I hope you sort of get the general idea. And using this technique and using what we said at the very beginning of the talk, namely that it doesn't really matter so much that this is coming from the left kernel of the stoichiometric matrix. We can put actually any sort of affine linear equations here and still get a rank condition. We can use that to say something about absolute concentration robustness. So let me begin by just recalling what absolute concentration robustness, or ACR, is. So we'll say that we have absolute concentration robustness with respect to one species, the ith species, if the whole positive steady state variety is contained in a hyperplane for that variable. Okay, and we also consider the notion of local ACR, which is slightly weaker, and it's saying that, well, there could be many, but finitely many hyperplanes of this form, such that they together contain the positive steady state variety. So for example, the positive steady state variety might have two pieces. So maybe this blue curve and this blue curve, and both of them are contained in a hyperplane with respect to the ith variable. So I guess it's maybe the y variable in this case. Then we would say that this is local ACR. And just like ACR, this really means that if we just perturb the total amount a little bit, it will not change the value of xi at the steady state. So it sort of corresponds to some sort of robustness to changes in the environment of the network, which I guess is quite interesting from a biological point of view. So the way we attack this problem is to say that, okay, we can first of all, let's assume that our network is in the non-degenerate scenario, in the sense that, well, there is this set of rate constants where there are positive steady states, and this is assumed to be full dimensional. So there's a nice open subset where we have positive steady states at all. Okay, and then we consider a modified system where we have taken the steady state equations and we have tacked on just a single linear equation like this, which we can think of as a conservation law, but it's not really a conservation law. It's just another type of linear equation that just keeps track of the value of the ith species And then we can form the corresponding subset for this conservation law, where the W matrix is just a single row consisting of the ith unit vector, and we can form this set, and we can think about the rank condition for this to be either full dimensional or lower dimensional. And it turns out that a network generically has local ACR. So for almost all choices of parameters, it behaves like this. If and only if the network is degenerate with respect to this conservation law, in the sense that this subset of parameter space is small, lower dimensional. Okay. Just to give you an idea of the proof, if we have local ACR, it means that this must be low dimensional, because we wouldn't be able to perturb K and C freely. So if we are in here, we have positive steady states, and the value of xi is C. Well, if we just perturb C a little bit, we won't be in the steady state variety anymore, because there are only finitely many hyperplanes that contain the whole steady state variety. So this would have to be lower dimensional. And conversely, if it is lower dimensional, then this has dimension at most R instead of R plus 1. And we know that the map from here to here is surjective, so we have something that's at most R dimensional. We know that we assume that this is R dimensional, and then by a geometry argument, this has to be a finite to one map. So for each K, there would be at most the finitely many Cs. That's a bit vague, but maybe you get the sort of the general gist of this type of argument. And that means that we can state this a bit more formally, that we have generic local ACR with respect to the ith variable, if and only if the network is degenerate with respect to this ith unit vector that corresponds to this matrix having rank less than the rank of the network plus 1 for all choices of V's and W's and H's like this. And if we just think about the linear algebra of this a little bit, we can simplify this a little bit by just subtracting the ith vector from here and really turn this into a smaller matrix, where we require that the ith column of this matrix should be removed, and that corresponds to removing the ith row of the kinetic matrix. Okay, that's a small linear algebra trick that we're doing. Yeah, and this is again a computer-friendly check that you can do to either prove generic local ACR or rule it out, because if this is not true, then it would fail for almost all choices of W. So probabilistically, you can just take something random in here and check what happens. Okay. And if we really want to go from local ACR to global ACR, well, then we would need something like that guarantees that the steady state variety, so a set of positive steady states, has a single piece. And this is something that we are currently working on from a more algebraic point of view. The first step would be to try to prove this over the complex numbers, and it's a very interesting problem that I would be very happy to talk to anyone in the audience who are interested in algebraic geometry about how we can attack this problem. A completely different way of going from local ACR to global generic ACR would be to think about this a little bit more algebraically instead of geometrically. And then it turns out that if we have generic local ACR in this case, then there is a witness of that generic ACR, in the sense that there is something in the ideal of the system. So the ideal of the system is simply the set of all polynomials linear combinations that you can take of your original steady state equations. You have to saturate to sort of get rid of redundant monomial multipliers. And if you take this set and look at all of those polynomials that only involve the ith variable, there will be one such polynomial. It will be unique up to scaling, and it will, in a sense, be a witness of the generic local ACR, in the sense that its positive solutions will, for each choice of the rate constants, will be the sort of these finitely many values that the ith variable can take. And if it turns out that this witness only has a unique positive solution for all choices of case, then that will prove generic global ACR. Of course, this is a quite heavy computation, but it could be a nice way to think about this theoretically from, like an algebraic symbolic computation point of view, because in principle you can compute things like this with Gröbner bases. Okay, I think it's maybe time to wrap up. So I'll just quickly mention that we are working on an implementation of this in Julia. I don't know if Julia is the right way to implement this. I'm very interested in hearing people's thoughts on where and how we should implement this to make it as accessible for like people in biology and chemistry as possible. But what's nice about Julia is that there is this catalyst package that where you can do lots of fun things with chemical reaction networks. So in particular, you can enter a reaction network, and then we have some code that checks if the stoichiometric matrix has a positive element. We have a code that checks the non-degeneracy condition and these local ACR conditions. And this is very fast. We've tried this on databases of chemical reaction networks, in particular this ODE base that is based on biomodels. The largest one with mass action kinetics has 300 reactions, and doing these checks it's a matter of seconds. So it's very fast things that you can do as a sort of an initial step when you're analyzing a chemical reaction network. And so to summarize, we developed these rank conditions that can check whether you are in a non-degenerate or degenerate scenario. If you're in the non-degenerate scenario, it means that there is an open subsetting parameter space where you have solutions, and the geometry is nice in the sense that it's a manifold of a single pure dimension everywhere. And if we're in the degenerate scenario, then there simply won't be solutions for most choices of rate constants, and the Jacobian will be problematic whenever we have solutions. And many classes can be shown to satisfy this condition, and we can also turn this into a condition for generic local ACR, which again is something that you can check very easily on a computer. So with that, let me thank you for your attention, and if there are questions, I'm very happy to answer those.
Thank you, Oscar, for the nice talk. So I'm sure it will be very good help before reading your paper. We'll be able to follow without knowing too much about algebra. But it also reminds us that it is worth studying. Let's see. Okay. So any questions, please? I will return to matrix W. It was a good choice to not to exclude the possibility to have another linear mass conservation law, not given by the kernel, because it may happen that there exists such a linear first integral which is which doesn't belong to the kernel of the stoichiometric matrix. In this case, it's also included here.
Yes, yeah. I mean, here we use this as a sort of theoretical trick to extend our results to generic local ACR. But yeah, I guess it's a good point that there could be biological systems where you sort of naturally have other conserved quantities that don't come from the. Do you have an example of this, or do you know like where this could arise? That you have other first integrals that don't
Yes,
come from the.
I will show you. Yes, there is
Mhm.
an example in one of the papers by friend, early papers. I will show you.
Yeah.
Regarding that,
Yes.
can you extend this W business to something that would be like, for example, non-linear? Say if you have a non-linear conservation law, because those happen too.
Yeah, that's true. That's true. There can definitely be nonlinear conservation laws. Yeah, I don't know. I don't know how if there is like a nice general structure that this higher conservation laws will follow. And I also don't know how interested we are in intersecting with those. Like I guess this is a philosophical question for like the whole field of chemical reaction network theory, that we're very focused on these linear conservation laws, and we use these to like define our stoichiometric compatibility classes. But it's quite rare, I guess, that one includes the nonlinear conservation laws. And maybe that's a question for the more.
Well, yeah, it's just there's a couple of papers where there's one paper where they use this thing called Dabou polynomials, DABOUX, to get some extra conservation, non-conservative conservation laws. Sorry, non-linear conservation.
Mm-hmm.
So I was just wondering if, in general, it's sort of hard to take advantage of that, but I'm wondering if we can use this sort of technique to get you some more information with that. Because this seems to be a more standardized way of trying to use conservation laws. And of course, with linear conservation laws, we have different methods. But I imagine for non-linear ones, it's pretty hard. And maybe this helps.
Yeah. Yes. I mean, somehow what's really crucial in our all of what we're doing in this line of work is that we want to have like a good grasp of what the Jacobian looks like. So when you have linear conservation laws, then it's super easy because it's just the matrix of conserved quantities. That's the Jacobian for the conservation law part of the system. If you have nonlinear equations, this is going to be more complicated, and it would require us to really I don't know. We should think hard about what the structure will be, or if there is a nice way of expressing it. And furthermore, it's going to be important that, because really what this is saying, I'm being a little bit vague here, but what I'm saying is that we should find a choice of rate constants and a choice of C's, total amounts, such that there is an X in that corresponding positive zero locus, such that this holds. And that's in general very hard to do, because we don't have like a parametrization of all the solutions. But when we have, in the case when we have the linear conservation laws, we can use these convex parameters to really get around the problem of having to find a parametrization of the steady state variety, because we somehow, well, I guess that's more, somehow we can parameterize the set of k's and x's that go together with these convex parameters that go back to, I guess, Clark and other people in metabolic reaction network theory, and that's somehow what helps us go from this complicated condition to this more computer-friendly condition. So that would also be a challenge with extending this to nonlinear conservation laws, because yeah, if this part is more complicated, it might not play so well with these convex parameters, and then I don't know what happens. But it's an interesting challenge. And I would also be interested in hearing more about where these nonlinear conservation laws are used in the applications, in the actual biology and chemistry, and how they are interpreted.
Other questions, Lima? In the meantime, I would like to ask you, Oscar, send me the slides. Can have it.
Yeah, of course.
Probably I will